Hello again, everyone. So this is going to be the small or short lecture on thermodynamics, which in your textbook is chapter 12. Okay. The idea with chapter 12, so it's not chapter 18, it's chapter 12. I'm just using my own set of slides here. But the topic is basically the laws of thermodynamics, or the first and second law of thermodynamics. The zero law, we went over that on the first class, the first video lecture, in which you have that if object A is in thermal equilibrium with object B, and if object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C, right? So it's sort of like A and B, B and C, then A and C are in equilibrium. Now, in this lecture, I'm just gonna go over some of the specifics for each of these sections. On the next video is where I'm gonna go over the problems, what you should be focusing from the textbook, okay? But the main idea with thermodynamics is to apply some of what you have done in ideal gases and heat and kind of combine together with the different processes. You see, that's the main thing about thermodynamics, is the isobaric, isochoric, isothermal, and adiabatic processes. For each of those, depending on the type of gas, you are going to have different values of heat, work, and the change on internal energy. So if we go to the first law of thermodynamics, it's basically written here. The amount of change of internal energy, delta U, is equal to the heat minus the work. Or in many textbooks, they just write heat equals to work plus the change of internal energy, which is basically the concept of conservation of energy, right? If, for example, you have an isochoric process where the volume is constant and you add heat, that internal energy increases. That's because there is no work. So you can have a container where you add heat, then the amount of energy, the internal energy of the gas, will increase. Okay, so the final state of internal energy minus the initial state is positive, that's equal to heat. So again, that's in a particular process where there is no work. So all the heat is converted to internal energy. But that's an ideal situation. If no, if you have work on the external world, right? Work done on the gas, and no heat is added, that's adiabatic. Then all the change on internal energy is equal to minus the work. So you have an insulated material where there's no heat on the surroundings, no heat is lost or gained. Then doing work like this decreases the amount of internal energy or energy of the system. If the piston was moving down, then it will be the other way around, and then the amount of work done by the gas is equal to the change of internal energy, which in this case will be positive. But again, this is an ideal situation when there is no heat added or lost. Adiabatic. So adiabatic, isochoric. And then when you combine in a general situation, you have delta U equals to Q minus W. What matters here is the signs of Q and W. Q is positive when you gain heat. Q is negative when you lose heat. That makes sense. Work is positive when work is done by the system. Work is negative when work is done on the system. Externally, internally, all right? So that's how you can think of it. The internal energy depends on the temperature. So in an isothermal process where there is no change on temperature, the internal energy change, the change of internal energy will be zero. So the work done and the heat added, however, depend on the process. Isobaric, isochoric, isothermal, or adiabatic, you have different values for heat and work. So in this case, if you are rowing like this, you are doing work, positive, you are burning calories, so you are losing heat, so your internal energy is decreasing. That makes sense. That's basically when you do exercise. You are doing work, you are losing, burning calories, and you are losing energy by doing that. That makes sense. That's basically the conservation of energy. That's a thermal process, if you think about it. So when we look at thermal processes, right, we are going to assume that they are reversible. For a process to be reversible, it must be possible to return from point A to point B or from point B to point A. Okay, and you're going to see that in what we call a pressure versus volume diagram. And there are some problems on the assignment where you have a PV diagram and you have to follow it. Depending on the type of process, there is a path that you're going to follow. Okay. For example, here, the gas is compressed by a constant temperature. So in an isothermal process, you are compressing the gas. So heat is leaving the gas, but there is no change on temperature. If you let it expand, it's drawing heat from the reservoir, returning the gas and the reservoir to the initial state. For that to happen, we have to assume the piston to be frictionless. Again, that's an ideal situation, right? So if you don't want to have any sort of temperature change, one of the factors is the piston not to have any friction, because friction at the end of the day is some sort of energy, heat, that can contribute to a change of temperature of the system. And you don't want that for this process to be reversible. So if you expand or compress a gas at constant pressure, which is possible in some cases, in some ideal cases, you have a pressure versus volume drawn like this. Now, keep in mind that pressure is going to be labeled in pascals or written in pascals and volumes in meter cube. So in here, you are increasing the volume, so the work is positive. The gas is expanding, so there is work done by the gas. The area under the curve, P delta V, that's the value of work. There is change on internal energy and there is heat added to the system. Okay, so none of the factors, none of the parameters, Q, delta U, or W are zero. However, in the constant volume, the isochoric process, the work is zero because of the definition of work. The definition of work is P delta V. So if there is no change on volume, the value of work is zero. So all the heat added or lost by the system, in this case added, is equal to the change on internal energy. And there are some equations that we are going to introduce that include the molar mass or the amount of moles, the specific heat capacity, and the change on temperature. Now, the specific heat capacity C or little c varies depending if it's a constant pressure or constant volume, if it's monoatomic or diatomic, right? You can have gases who are monoatomic and gases who are diatomic. Depending on that, you have different values of heat and internal energy. If the temperature is constant, you have a curve like this, okay? And all the value of heat is equal to work. There is no change on internal energy. So the pressure varies inversely with the volume. Now, how do you find the work? I want to show you that in the whiteboard, next video. But basically, if you use the ideal gas law, right? So PV equals to nRT, right? Now we know work is P delta V. Now in calculus, we can say that d work, the differential of work, is P dV. Now P is, or P is nRT over V. So you put in here nRT over V dV, and you basically integrate from initial volume to final volume, and you get work equals to, so if you integrate on both sides, of course, nRT natural log of V final over V initial. Now, I don't expect you guys to do the calculus here, but at least use the equation here. So the equation depends on, the word depends on the natural log, right? So that's because of this calculus I just did. Here's the equation now. Okay, the area under the curve is this. And in an adiabatic process in which no heat flows into or out of the system, the PV diagram is also a curve, but all the work is equal to negative the change on internal energy. That's because Q is equal to 0. So here it is a summary, right? Adiabatic, constant pressure, you have your first law of thermodynamics, Q equals to delta U plus work, P delta V. Constant volume, the work is 0, so Q is equal to delta U. Isothermal work is equal to Q because delta U is 0. And adiabatic work is equal to negative delta U because Q is 0. So in most of these equations, you need to know how to calculate Q or delta U. So that is when we start using this QV and then QP. What's QV? Is the value of heat at constant volume, where N is the number of moles, CV is the value of specific heat capacity at constant volume, and the change on temperature. Now, constant volume work is 0, so this Q is effectively equals to the change delta U. Okay? And the nice thing is that this is delta T. So if you want to find U initial, it will be N CV T initial. And U final is N, the same number of moles because conservation of mass. CV is a constant, T final. And I'm writing these equations because you're going to find problems on the textbook where they might ask you for the internal energy at a specific time, at a specific value of temperature. So that's how you do it. Okay? Now, at constant pressure, NCP delta T. But at constant pressure, there is work, right? So you cannot just say that this is equal to delta U. So you have to solve for delta U using QP. So that's the value of heat at constant pressure is the work plus delta U. And work, we know for constant pressure is just P delta V. Okay. Now, I'm going to show you in problems that there is a way to find this delta U even if you don't have work. There is nice ways of finding delta U for constant pressure as well. Now, Cp and Cv are constants, as I said. For a monoatomic ideal gas, Cv is 3/2 of R, Cp is 5/2 of R. I want to write here for a diatomic, is you may have that for diatomic, right? For example, oxygen 2, that's a diatomic ideal gas. Diatomic, yeah. Cv is 5/2 of R, and Cp is 7/2 of R. How do I know that? Well, Cp minus Cv is always equals to R, by the way. That's how we know, right? That's always true. So for monatomic, that works. Of course, for diatomic, also that works. All right. And why is that important? Because you may have diatomic, monatomic, and because if you have CV and CP, and we go back to the equations, let's go here, I can find the value of heat and internal energy. And here I can find the value of heat. And if I have change of volume, I can use ideal gas to find pressure, I can find work, and then with those values of Q and work, I can find delta U. This is a CP and CV for various gases, depending on the type of gas. Remember, since this depends on the value of R, and then we can see, right? Depending on the type of gas, you find that. Again, oxygen, nitrogen, they are a little bit higher because of the definition of CP and CV, but they are normally always close to R. For an adiabatic process, it can be proven that P and V vary in a curve like this. And you can find the value of work. You can find the value of work because you basically, you think about it, D work is PdV. But P is a constant. Let's use constant K over V to the gamma dV. So if you're going to integrate on both sides, that's a constant. And here you have an integration via the minus gamma, via the gamma minus, via la minus gamma minus. You're going to integrate this. There. Right? You do the derivative. Yeah. So that's basically, so if, depending on the gas, you have to find this constant. Although this constant is just this. So you can just say that work is PV to the gamma minus 1 multiplied by V 1 minus gamma over 1 minus gamma. Right? And then here, you will just cancel this and then you can just find the value of work. That's if you want to find the value of work. Right? But sometimes we don't need to worry about that because we have the gamma, since gamma is defined as Cp over Cv. So we have the exponent here. So if you have the exponent, then it's sort of like irrelevant, right? We can just find the behavior of the adiabatic process. For monatomic, that's the case. For diatomic, will be 7/2 of R over 5/2 of R. So 7 over 5. So gamma changes depending on the type of gas. And when we do the problems, you will see how we can use all of these parameters. All right. The second law of thermodynamics is basically the application of the first law in heat engines, thermal machines, and the Carnot cycle. Right? A heat engine is a device that converts heat into work. Right? This is a classic example where you can use a piston. It's a steam engine. Fuel hits the water, the vapor expands by that heat, and does work against the piston. The vapor condenses back into water again, and the cycle repeats. So you have a hot spot, a cold spot, and basically the work done by the piston, which then can be replaced by an engine. All right? You have a hot reservoir, a cold reservoir, Tc, Th, Qh by Th, Qc by Tc, exhaust heat, heat added to run the engine, and the work done by the engine. So that's the work, that's basically what you use. So work is QH minus QC, right? Or QH equals to work plus QC. Energy in is equal to energy out. Out, out, in. So whatever is going towards the engine is equal to whatever is coming out from the engine. So there is an efficiency here. The efficiency here is given by the work done by the engine, by the heat added to the engine. And that's always less than 100%. The idea with a Carnot cycle is to maximize that efficiency. And we can maximize that efficiency by using the Carnot theorem, which uses two isothermal processes and two adiabatic processes. The isothermal process ensures that there is no loss of internal energy, and the temperature is constant, of course. The adiabatic process ensures that there is no loss of heat. There's still some work. So there is still, you still have no 100% efficiency, but you're maximizing it by ensuring that you have that two isothermal and two adiabatic processes. So then the efficiency depends only on the temperature values of the hot and the cold spot. Okay. Again, when we do problems on this, you're gonna find that this is actually very simple. It's a nice application of the first law of thermodynamics. If the two reservoirs are at the same temperature, the efficiency is 0. The smaller the ratio of the cold temperature to the hot temperature, the closer the efficiency will be to 1. So basically, you don't want to have a lot of heat loss in the exhaust. Now, heat normally goes from hot to cold, as you have seen from these heat engines. However, you can have refrigerators, air conditioners, where heat pumps use a work transfer, right? Or you go from cold to a hot object, right? So if you compare the heat engine to a refrigerator, you will see that the value of QH now is equal to the Q in the cold spot plus work. More heat is exhausted to the kitchen than is removed from the refrigerator. All right, that's what you ideally want in a refrigerator. And in here, you have the coefficient of performance, not the efficiency, which is QC over W. The efficiency was W over QH. The performance indicator for a refrigerator is given by the heat in the cold spot divided by W. All right. Typically, you want to have this between 2 and 6. So the process is basically inverse. You go from cold to the air conditioner, warm to the air conditioner, then you have QH going from cold to the hot reservoir. Exhausting and air conditioning within the house will result in the house becoming warmer. Just as keeping the refrigerator door open will result in the kitchen becoming warmer. If you didn't know that, now you know. If you open the refrigerator, you inverse the process of the refrigerator, making the room where the refrigerator is warmer. A lot of people don't know that, but you can learn that by experience, and you will see how actually that works. So here's the same equations that we did for heat engines. And then we finish with entropy, which is the third, or in some cases, the second law of thermodynamics, where a reversible engine has the following relation between heat transfer and the reservoir temperature. So QC over QH equals to TC over TH. So QC over TC equals to QH over TH. So that ratio is always the same in a reversible engine. And the definition of entropy, which is basically the value of disorder of a system, is equal to the heat, right, divided by the temperature of the system, right? In a reversible heat engine, it can be shown that entropy does not change. That's because it's reversible. All right. The total entropy of the universe increases whenever an irreversible process occurs. The total entropy of the universe is unchanged whenever a reversible process occurs. That's the second or slash third law of thermodynamics. All right. So yeah, entropy can be thought as the increasing disorder in the universe, or in this case, of a system. All right. So there is not much here to say. We will go over what the textbook has to offer on the next video. All right. The major thing on this chapter, and you're gonna find on the assignment, is heat engines, refrigerators, and then geothermal processes, and how we use the equations of heat, internal energy, temperature, and a little bit about entropy in the wave assigned problems. Again, if you go to assignments, you can find problems on this on chapter 12, the laws of thermodynamics. So basically here we conclude the topics for the first exam and the topics for temperature, ideal gas, temperature scales, heat, specific heat capacity, and thermodynamics. What's coming next is vibrations and waves, waves and sound, and then we start going into light and some applications of electromagnetic waves. So expect the next video. Well, you probably will see it once you start watching or going through these lecture videos in here. All right. And then please make sure after you go over 10, 11, 10, 11, and 12, you start preparing for the first exam. So without further ado, I will see you guys later. Have a nice rest of your day. Bye-bye.